All right, thanks, Eddie, and thanks everyone for being here. I wanted to say if you're sitting in the back, you might want to move up. I'm going to be showing some videos of demos up here. You might want to be able to see the screen. Should be pretty cool, I hope. Anyway, I'm really excited to be here talking to you. It's a great opportunity. And I want to tell you today about Batfish and PyBatfish, two open source projects we work on that will help you validate your networks. So really, engineers today are being asked to do increasingly complex tasks at increasing scales. So more devices, more types of devices, more deployment scenarios, whether it's on-prem, whether it's across site, whether it's hybrid clouds, integration with more systems, automating things, more and more types of audits, building out entirely new data center designs now that you see the next generation needs to be different. And my claim is that the existing tools we use for this really don't suffice. So we have a lot of great monitoring tools, but what monitoring does inherently is find a small class of specific bugs once they're in production. It's incomplete because usually you're only finding the bugs that you're looking for, and it's reactive because you don't actually find or fix these issues until they've already taken effect in your network. Then there's operational state validation, where you actually collect and verify router runtime state. Maybe use Ansible to log into all the devices. Again, this is incomplete because you're only able to verify certain properties, certain things you measure. And once again, it's reactive because anything you can find from this runtime state validation is already affecting your network. There are some approaches that are more proactive. So you can emulate a change where you take a partial impact, you take the change and you deploy it on a partial subset of your network that you've spun up in VMs, say, and you can get a good sense of a partial impact of that change. You can spot check some things you want to happen and make sure they do. This is, again, a manual process. It's resource intensive. It's, again, incomplete because you're only able to rely on the part of the network you're able to spin up, the part of the properties you're willing to check, and often the limitations of the specific VMs the vendors make available for you to try your stuff out. But at least it's proactive. At least you are doing this test before the bugs hit the network. However, I claim we need something better. We want tools that are both proactive, so you're able to run your checks before your bugs hit your network, and they're comprehensive. Rather than checking just the bugs you look for, they can find entire classes of bugs with very general search parameters. And I'll show you some demos in this talk that explain a lot more what I mean. The project that powers all the stuff I'll be talking about is called Batfish, and it's a suite of tools for proactive, comprehensive, and automated network analysis. It's an open source project. It's under the Apache 2 license, which means all of you can try it out. It's used in production by multiple Fortune 500 companies. And its contributors these days are IntentionNet, the company I work for, but a bunch of other organizations making real changes to the code for their own uses. This is a real open source project. So I'm going to explain to you in some demos and some slides the kinds of things Batfish can do and how it works. So here are 4 of the core capabilities of Batfish. Batfish can help you audit your configuration settings. So check whether devices are compliant with site standards, check whether cross-device configurations, such as BGP or IPsec sessions, are compatible with each other. We can also do data plane analysis to say, how does traffic flow from A to B and why? And if you mix those two together, now you can see we can ask questions like, will all my tunnels come up? These, again, are still very sort of monitoring-related checks. You can do this by just logging devices and dumping their config, dumping their ribs, this kind of thing. However, Batfish can also do a bunch of comprehensive reach checks. So for example, our comprehensive reachability analysis can answer questions like, can any flows violate cross-site isolation? Not just the flows I'm looking for, but is there any possible packet that will do this? Or can ensure that all clients can reach my DNS server. We can also do comprehensive analysis over things like ACLs and firewall rules. So for example, given an ACL definition, does every rule in here actually matter? Or did I mess up the order of my ACL so that some of my rules that I think are doing important things for me are actually totally unused? And you can do analysis of firewalls where you can say things like, tell me every single flow that can get from outside the network to inside the network. And you can constrain these things and you can iterate this to build some really cool analysis of your network. I'll do some demos of all this later. So once you have these capabilities, and there are more I'm not going to get to talk about, how can you use Batfish to be proactive about your network? So one thing you might do that we're really trying to encourage everyone to do is to build a CI/CD pipeline for your network. So you can do proactive analysis of your network by testing out changes you're going to make before you deploy them to your network. And you can do continuous testing of your network by, for example, downloading the running config every night, seeing everything that's different, making sure that even if someone manually logged into the devices outside the scope of your normal workflow, that those changes have not messed up your network in terms of its configuration correctness, its compliance, or your security and reliability policies. On top of that, you can use Batfish to do what-if analysis to test specific scenarios you're interested in. Maybe you want to do maintenance, maybe you want to check that you're resilient to failures, maybe you want to investigate device recovery. You can do all of this by just mocking up that type of scenario in Batfish and testing what would happen without actually impacting your running network. So I've told you what Batfish can do, and I'm going to tell you how it works. One thing to take away here is that the only thing Batfish needs is offline data. So the primary form of input is the raw configuration for your networking constructs. Your show run configs from your vendors, your JSON or XML dumps from your clouds. If you have a Linux-based or white box system, you know, the IP tables rules and other config like that. And from that, Batfish is able to parse each of those vendor configurations and then build a unified vendor independent model. So say we have, you know, in Cisco iOS devices, you might configure BGP using template peers, using route maps, using access lists. And on Junos, you're using BGP groups, policy statements, and firewall filters. We parse this configuration, we abstract it out, we unify it into the Batfish model, where we only need to reason about BGP sessions, routing policies, and ACLs. And again, I'll show you how this works later. So just as an example, on the left I have iOS config, and on the right I have Junos config for BGP. And the blue lines I've highlighted are roughly equivalent configuration across the two languages. And in the internal data model for Batfish, which users are not normally exposed to, but I'm putting it here for your benefit, we've unified this all into a single JSON structure where we have the details of AS4, we have, you know, we're aware of the vendor-specific defaults that we know and honor. We can track things like which import policies or export policies you use. And we can also build an aggregate export policy that captures all the details here, not just of the particular prefix list or route filter you use for your export policy, but also vendor implementation specific details like default originate. Now that we've done this, we now have you know, a unified model of all of your networks, devices. We know how they're connected, and now we can do a routing simulation. So we actually go through and simulate the routing of all the protocols that you're running in your network. We get the ribs and fibs for all devices. And now we know how traffic will flow through your network. Finally, we have a network verification and query engine that reasons about your network, right? Unified model on the left, ribs and fibs in the middle, and on the right, we now model your network and your network policy as a system of mathematical equations. We put this together, and we can reason about all possible traffic sources, traffic destinations, the actual flows you're sending, how things might fail, route advertisements you might receive. We can reason about all possible of these things and answer questions and ensure that your policy is honored under all these conditions. And this is a very small summary, but Batfish finds real bugs in real networks. So our users have automatically detected bugs in things like misconfigured servers, misconfigured ACLs, where, for example, in one case, they were mixing iOS and ASA masks in their ACLs. And so they thought they were allowing a single IP. They were actually allowing all. And you know, it's really hard to notice when things are failing open because everything still works. We found configuration bugs where, for example, BGP sessions couldn't possibly come up because the two sides weren't configured compatibly, or where the BGP sessions couldn't come up because there was an ACL in the middle blocking them from being established. We've also found things like multi-path consistency, where even though I have ECMP in my network, the flows have different dispositions. You know, some fail, some succeed, based on what paths they take. The net result of this is inconsistency, increased latency, reduced capacity, fragility, and security holes that you just don't know about until someone finds them. Hopefully it's you. So in the next section, I've got a series of demos showing all the things I've talked about so far. For this first set of demos, I'm using a sample data center network. It's a realistic network. It has 67 nodes. It's a mix of Juniper and Cisco devices. There's 2 pods here on the left and the right. We also have 4 Linux servers in different parts of the network. The EGP and IG, you know, we're using BGP and OSPF to route traffic throughout the network. The Linux devices use IP tables. And this is modeled on networks we've seen in production. So the first use case, I told you Batfish can help you audit configuration settings. So in this demo, I'm going to be using a Jupyter notebook to drive the demo. And this is a pre-recorded video. So Jupyter notebooks have become a way that people do data science in modern environments. It's Python basically, and you get to interact with it. So the first thing I've done is I've just run some setup scripts to import the PyBatFish libraries and to customize data output. Let's go look at the input. So if I just list the config files, you can see I have a bunch of show run output from a bunch of different devices. We have border routers, core routers, distribution layer, firewall, storage, things like that. Let's go look at Tor2A in the Seattle 2 network. Right, this is a Cisco NXOS router. Let's go look at Tor2A in pod 1. This one is a Juniper router with apply groups and multi-chassis lag and all those things. So what BatFish does is it takes all this configuration as raw input, and then we're just going to run we're going to initialize the snapshot from those configurations. And what BatFish has done is read all that config. Since I didn't give it topology, we'll infer topology based on the L3 configuration here. And the first thing I run with a new network is just to see, did BatFish find anything interesting during initialization? So these are 3 issues we see fairly commonly. They may not be issues at all, actually. We see empty prefix lists on a couple of devices. This is fairly standard. You don't have anyone malicious yet, but you might later. So you leave a hole and you put them in your policies. This is fine. We also see one interface has EIGRP settings. I think the delay is configured. But since EIGRP is not running on that device, we're just letting you know, hey, you may have some orphan configs here. It could be that you didn't attach this to the process correctly, or this is just old data you don't need. So I mentioned that BatFish gives you a structured vendor-neutral data model of your configuration. So here I'm running the node properties questions, but you can run this for OSPF, BGP, interfaces, sessions, IPsec, MLAG, lots of other things. For each one of these properties, we give you a table of the output. Note that the input here was from completely different vendors, but we've put it all into one unified table. So I think I'm showing you 5 rows of the table here. We see one of our Linux servers and 4 of the Juniper devices. We have a canonical IP like the loopback. We know which DNS servers are running. We can see what domain name is configured, what device type everyone is. And there's a whole bunch of more properties that some devices have and some devices don't, in terms of which ACLs they have defined and so on and so forth. Even with something simple like this, we have now taken a bunch of different device complexity and put it all in one queryable format. So you can ask questions like, for instance, how are the logging servers configured throughout my network? So this line of code, line 8, is a standard pandas query. So we have a pandas data frame, which is a standard Python data science library. And I'm just saying, for every device, pull out its host name and the logging servers, and then show me, for each unique configuration of logging servers in the network, show me all the devices that have that configuration. So we see that the Linux hosts don't have logging servers configured. They're Linux servers. And then we have 4 different types of devices here. Every device has this 1065, 1420 NTP server. And in all the groupings but one, there's actually 2 servers configured. Maybe that means that these 2 storage devices in pod 1 are misconfigured. And then you can again see sort of role-based assignment of servers to the different devices. This is not meant to say anything super deep, except to show you that we are able to provide a lot of insight into your different configurations and actually find useful relationships and potentially bugs based on that. So the next thing I'll talk about is the data plane analysis. So in this video, what we're going to do is start with our ribs and fibs we simulated, and then we're going to go run a trace route. In this particular cell, I'm going to simulate routing from traffic leaving from Tor 1A in pod 3, going to quad 8, which is Google's OpenDNS server. And essentially, I've asked in this query, I'm running trace route, and I'm saying start from pod 8 with the destination IP of Google's DNS, and give me up to 3 traces in the case of lots of ECMP. If we scroll down, we see the start location, end location, or end IP I specified. But we also see BatFish automatically populated a reasonable source IP and decided to use a UDP trace route. And then on the right, we can see what happens to this flow in the network. So this particular flow is successfully exiting the network at the firewall. It starts on Tor 1A. It's forwarded out using this particular IBGP default route. It follows these interfaces and follows these other routes through the network. We see IBGP, BGP, OSPF, external type 1. Eventually, we see traffic reaches the firewall, where it is accepted by the outgoing security policy on R80.6, which is basically the inside to outside zone policy. And we see on the right that there are 32 traces there. So ECMP is active, and there were 32 separate paths on the network. And we can actually tell you about all of them. So this first trace is going from Tor 1A. It's going through the spine, then core 1A, then border 1B. If I look at the next trace, we'll see this is the spine, core 1A, but now border 1A, not border 1B. And the next trace, I think, will go through core 1B. So we're able to show you very fine, low-level details of exactly why traffic went from A to B in much finer granularity you're going to get out of, say, running traceroute for real. Because we're showing you all the routes matched, all the interfaces taken, all the ACLs traversed, and things like that. Now, I'm also going to run the reverse traceroute. So I'm going to say traffic coming in from that external interface on the firewall with a destination IP, where I just copied the source IP from the previous flow. In this case, we see that the UDP flow is actually denied. So it comes in the firewall on RE 0.6, but when it tries to send it out, RE 0.5, to inside the network, it's denied by that security policy. We'll actually dig into this a bit later. So the next edit, right, I showed you traceroute, right? Traceroute is great for understanding what is happening in your network, what paths flows are taking. But now let's do something more comprehensive. So in that last example, I showed you that a standard UDP traceroute originating incoming at the firewall was not delivered to that TOR. However, does that mean that no traffic gets through to that TOR? Of course it doesn't. All we did was try UDP traceroute, right? A single flow. So now I'm asking, is there anything at all, any packet that satisfies the constraint that it starts outside the firewall and it is destined to that TOR? And here, Batfish was able to find a flow. It found that this particular source IP, which is configured as the other side of that firewall, the other side of that interface coming in, using ICMP, if that packet happens to be sent, the flow will be accepted. You can see there are 200 paths through this network. I don't know exactly why that is. You can see, again, exactly which routes are taken. And you'll notice that the only information I seeded this with was where the traffic starts and what the destination IP is. Batfish did the rest of the work to find all these results. You'll notice here, again, that this time it was accepted or permitted by the security policies to RE 0.5, and we'll dig into that in just a minute. So that brings me right to the comprehensive ACL and firewall analysis that Batfish can do. So we saw that this particular packet, which Batfish found, without me telling him what to look for, found that a particular ICMP packet with a particular source IP, dest IP, and coming in a particular interface is delivered. Now let's try to understand why. So here you can see that I'm running the test filters question, where I've set up just those constraints that I copied from the previous output. And when we run this, it's going to explain to us why was this packet accepted. I'm a little ahead of the video, sorry. So what we see is that this flow, in particular, was permitted by that security policy. Well, we knew that already, but why was it permitted by that security policy? In this case, the second line in that policy is the Juniper device's outside to inside zone policy, and that it was allowed by that policy. Now let's recurse. Why was it allowed by that policy? We don't yet know. It turns out the fourth line in that policy is, and this is a little complex notation, we're making it prettier, but in essence, that it matched a particular global address book, it's ICMP, and it came from the right source interface. So let's recurse again. Now we understand where the ICMP part and the interface part came from, but let's see what this address book means. So it turns out this particular destination IP is permitted by that address book because it matches the first line in the address book, which is in reference to another address book called Global RFC 1918. And then that reference itself is matched by another global address book, or some sort of address group, that is, which is Global RFC 1918-10. And then we can see now, OK, what happened is that this particular flow has a destination IP in the 10.0.0/8 private IP space. So we were able to use Batfish's deep understanding of the firewall rules to actually dereference complex behavior that Batfish automatically discovered for us, following it through many nested layers of transitive policies, taking into account the aggregate firewall policy on the device. I'm next going to show you a different type of ACL analysis we can do. And this is a very simple question, filter line reachability, that just says, look at all the ACLs in my network, and you can constrain the search, and tell me whether any of those lines are not having any effect, because every traffic they would handle has already been handled. So for instance, on these two TORs, line 80 says permit any OSPF traffic for particular /32 destination IP. But line 70 says allow any OSPF traffic from any source, any destination. Obviously, this line is not useful. Why do we think we needed it? Maybe it's old config and we added the allow all later. Maybe we added that allow all for debugging once and forgot to remove it. Maybe we should investigate. However, there's this other column called different action, which tells me when the first line and the second line would do different things to the flow. 2 permits is probably okay, but a permit following a deny means we're not allowing some traffic we thought we wanted. So in this case, there's a rule called allow all ICMP traffic from Seattle, and we want to be allowing it through this border router. But we're actually blocking it, and we're blocking it due to a rule called block RFC 1918. And you can see because the different action column is true that this is, we're denying traffic we thought we should allow. So let's just go quickly look at the configuration. We can see that the blocking term just says take any traffic with a source IP in a private address space and drop it on the floor after counting it. But the policy we have here, this allow all term, actually says, well, if it matches this particular source prefix list and it's a particular ICMP type, then let it through. And if we, again, go and dereference that source prefix list, we'll find out that prefix list is in IP address space. So we have one rule that's just saying block everything with a private source IP, and another rule saying allow specific ICMP packets through. That second rule is not taking any effect. It's meaning those ICMP packets we thought we wanted are being dropped. Maybe this doesn't matter at all. Maybe when there's an outage and I'm using ping to debug my issues, I'm not going to be able to find them because this rule I thought was allowing traffic that I wanted for debugging is not there. So I've given you an overview of those 4 Batfish use cases, or 4 Batfish capabilities. Now let's talk about how they can be put to use. So in this first demo, I'm going to show you continuous integration. Namely, how can we actually test Batfish changes before we deploy them? Or test network changes with Batfish before we deploy them. So we have some changes we want to make, right? We talk to our peers about what we're going to do. I'm going to log into this device. I'm going to change this config. We might emulate things. We might not. And then we'll deploy them. We'll probably do some lab tests. When we use Batfish, we can do all of this ahead of time, and we can be proactive and comprehensive when we're doing it. So in this video, I've set up a sample GitHub repository with network config and some tests and things like that. The network we're using is a very simple network. It has redundant border, core, and spine routers, 2 application servers attached to a leaf host. And what we want to do in this change is cost out that core 1 router. This network's running OSPF, so I'm just going to raise the cost on core 1. And I'm going to do that by just changing the config right here. Right? A typical network mop actually involves, I'm going to log into this device and run these commands, the net effect of which is to change these configs. Maybe you're using something like openconfig and you can just upload configs, do a config replace instead. But at a high level, what I want to do is change these OSPF costs. So I'm going to go cost out core 1. I'm going to create a branch, cost out core 1. And I'm going to propose this change to someone else on my team. And now using the standard interface, whether it's GitHub or Bitbucket or some other tool you choose to use, I can go, OK, this is the change I want to make. When I'm done with this change, all these costs are going to change. Sounds safe, right? That's the right way to cost out a device. But does it actually, can I actually deploy it or not? So I've integrated with another system called Travis that spins up a virtual machine, downloads the configs, downloads Batfish, and then runs some tests on it. I'm happy for the video here because it's speeding up through a minute of VM booting up. But in a second, what we're going to see is this yellow bar, which says in progress, switches to failing. So actually, costing out that device, as we said, did not succeed. And so one of the policies I have in this network is called test reachability. And so I expect that there's no reachability loss when I cost out this device. In this case, it found a flow that says, hey, if you start this particular packet on border 1, destined for the web server, it now goes through core 2, but which we expected. But at core 2, it's being null routed. And there are other variants of that happen at different versions of the network because of ECMP. So without anyone else having to look at this, even though I correctly configured core 1 to cost it out, we found a bug. Now I'm going to go back into core 2. And I made this example a little easy for the purposes of this demo. And hey, we have this old static null route lying around we didn't want. We actually had all the information in the previous slide where we saw that it was null routed and that it was following this particular static route. So let's just delete this route here. We added that for debugging some time ago. We don't want it. We make a new proposal for a new change. We update our proposal, I guess, really, with the aggregate of both changes. And then we again say, OK, here's what I'd like to do. So the same thing's going to happen, right? I've automatically created a new version of this proposal. The first one still, remember, we know why it's failed. We can get the links for why it failed. And the new one now is going to run for a little bit and pass. So now there has been fully automated analysis here, finding out that even a correct change had hidden side effects because of lingering config on some other device. We were able to find it and fix it without even a human needing to get involved in that initial review. And this is the type of thing that initial review probably couldn't have caught because it was a problem on some other device. Finally, let's talk about what-if analysis. So in this case, in that original network, we have a firewall, we have redundant border routers and core routers. We believe those routers are redundant. So what happens if one fails? What I've done in this first command is use the fork snapshot command. So based on the snapshot that I uploaded at first, let's now also fail border 1A. Then I can run the same question I showed you in Travis, which is, was there any change in reachability in my network when this device went down? So I'm just comparing reachability between that Tor and Google on the border 1A device. And lo and behold, I found no change, right? That means that at least for this particular space of flows, all flows that were delivered before are still delivered. All flows that were blocked before are still blocked across all types of packets, TCP, UDP, ICMP, et cetera. However, we can also see what changed. So I can run the route question and say diff the route tables for me across these devices. And we'll see some routes are only present in the original snapshot, the reference, the one we're comparing against. Some routes are present in both, but maybe lost to other variants of ECMP. And then a bunch of routes were lost. And again, this is now, again, a standard pandas data frame. So we can also do some other analysis in a second. For instance, figuring out how many routes were lost on each device. You can see, of course, the most affected routes were on border 1A, the device we took down. It now has 0 routes. But the paired border router, the firewall, of course, is directly attached. And then a couple of the layers nearby also saw their routing tables impacted by this change. However, we know there was no reachability change, at least for that search we did above. So we still know this is safe. We can also start to analyze what types of routes were impacted, right? So we see, the majority of the changes were in OSPF, external type 1, E2, and intra-area routes. And so, you are now able to get a sense of, here's a change I want to make, what types of things, ensure my properties still hold, and then also let me investigate ad hoc, in an ad hoc way, what types of things are going to be impacted. So I also want to emphasize that getting started with Batfish is pretty easy. So it's one line of Docker to download a container that will spin it up, both spin up the server and spin up a Jupyter notebook for you to try out on your own configs. And every single demo I gave you today has a longer form in both a notebook tutorial and a YouTube video that you can watch that gives you, where I did you 1 minute, you might get 5 or 10 minutes to explain more about how you can do these types of analyses and more. So with that, there are lots of ways to get in touch, become part of our community. Batfish is a serious open source project. You can join us on Slack, on GitHub, come to our website to find our videos and other links. And yeah, thank you, and I'm happy to take your questions now.
Hi, this is Shagifta from Facebook. I have a quick question that you have been running this test on the configuration and be able to find the bugs. Have you maintained the list of the bugs that you have found so far and work with the vendor like Cisco or Juniper?
So let's see. So the list of bugs we found usually are in configuration bugs, right? Customer configuration bugs. So that's not typically something we service to the vendors themselves, customer and user configuration bugs. And then in general, I can give lots of stories of bugs we found. We don't have a public list. I think there's a lot of sort of proprietary data locked up in there, but lots of bugs. I'm happy to talk offline.
Okay.
Hi, Avi Friedman from Kentech. I have almost the opposite question, the two questions. One is, have you thought about integrating this to some extent with actual virtual router software to find bugs? Because if you're modeling, you're assuming they actually implement it correctly, which we know doesn't always happen. So can you combine the kind of config bugs you find with interaction with vendor bugs? And the second is, have you done any work looking at playing traffic through the model rather than an all points potential, but looking at sort of these are your actual historical flows And I have a bias because that's where I come from. But we've been looks very cool. We're going to take a look, and it's very interesting. Those are the two questions that I have.
All right, let's see if I can remember both questions. The first question was, have we integrated with the actual sort of virtual routers software themselves? I would say this technology has been used to actually find vendor bugs, and those have been reported back. I'd say the Batfish itself is a little bit more of a core technology than that, so that's something we build around it. But that's absolutely completely doable. So we do, and people have used Batfish to actually validate lots of other types of systems for implementing things. And as you alluded to, it is a bit of a symbiotic relationship at times. And then your second question was traffic matrices.
Playing back historic traffic to say, would any of this, not potential traffic from all points, but my actual traffic or application workloads, playing through the model?
Right, so we have used traffic data, for instance, to, I guess one question would be, why would you want to limit your search when you could search everything? Is it mostly performance?
Well, if you're actually looking out to the internet, which I guess is the third question, but we can take this offline, is then, it's hard to simulate all potential things. So if you're actually saying that you can simulate every single kind of potential thing, I guess the question is, what's the baseline, right?
Sorry.
Because
when we're looking for all possible things, we're not actually enumerating all possible flows. We are doing mathematical proofs that, this particular space of flows, and we cover everything. So we don't have to limit our search space because we can actually, it's
but
fast
how do you know
enough.
what's broken? In other words, my network worked at this state, it was configured this way, this is my actual traffic. Now I've changed my network state and maybe correctly, but it breaks something which is an application flow. How do you know that from just the config?
If there's Batfish is there to validate your configuration errors, right? So if your configuration has resulted in a changed network, then we can run your trace route or whatever. If you've triggered are you talking about like triggering a vendor bug?
No, this is more, we'll take this offline.
Okay, let's take it offline. Okay. Thanks.
So please, cutting the mics here. Please keep your questions brief so we have time for the next presenter.
Jay Hennigan with Impulse. You mentioned that you can take the running config from a vendor and Batfish will then convert that to a generic config that Batfish understands. Can it do the reverse? Can I take, for example, a Cisco config, run it into Batfish, and output it as Juniper or vice versa?
Right, so the question was, can we then compile back into vendor configs? The answer is maybe, not yet. So what we found in practice is that our integrated model is a little bit simpler than the vendor models. So you may, for instance, you can configure your BGP templates 20 different ways at 20 different layers. We integrate that all into one data model. So we can, suggest like, hey, this MTU is wrong, but you might want to fix it at 10 different layers. And that'll be config dependent.
أنا أستار شام with Nutanix. So can this tool model any configurations? Does it support MPLS, VPN, and IPv6?
The feature set is very much user-based, so based on user demand. IPv6 is a straight line from what we already do to implement it, but there hasn't really been asked for it. VPN, the support is there to varying degrees, depending on what specific features you're looking for. So we can definitely tell you, for instance, whether tunnels come up. And MPLS, I think the support is pretty shallow right now. We've mostly been working in the enterprise space, but this is definitely all work that we know how to do when we have time and demand for it.
Okay, great work. Thank you.
Alan Hannon, CrowdStrike. I think my question overlaps, but I was going to ask if you do flow placement or volume of traffic.
So currently we're staying away from sort of any TE performance type analysis. So we can tell you, so we definitely don't do any at all flow allocation, load planning, that kind of thing.
And then a follow-up question. You mentioned earlier it's open source, but you don't publish bugs. Can you explain that to me?
Sorry, we advertise bugs in our own software. I'm saying we don't publish the bugs our users encounter in their own networks because that would be revealing information
Not about
their
your
networks.
software, but the customers' bugs.
Yeah.
Makes sense. Thanks.
Sorry.
Andrei Hemenkov, Athena Health. The first question is very short. You showed a list of vendors and like one at the beginning of the slides, one of them was Cumulus. Is that implied that Cumulus is supported as one of the vendors that?
We're working on Cumulus right now. It's not fully there yet, but yeah, talk to me after.
Okay. And the second question is, as network engineers, we're very much used to conf-t and CLI and doing things one at a time. What is the skill set that is reasonably expected from a user of Badfish? Like knowledge of Python, knowledge of CI/CD, like what are these development skills that are reasonably expected?
I think we're trying to make the bar as low as we can. I think the Jupyter notebooks and the Pandas data model, it's kind of the standard entry level like Python data science stuff that you'll get if you're joining Silicon Valley in any number of roles. I do think some basic Python fluency is really helpful, but also from the enterprise point of view, we're building even easier to use tools.
Okay, thank you.
Thanks. Thank you, Eddie.